So thank you very much for giving me the opportunity to speak at this very nice conference. I want to speak about the sum of digits function in linear recurrent number systems. And this is a joint work with Jörg Duswaldner from the University of Leoben. And first I want to study the sum of digits function in general numeration systems. Then we introduce linear recurrent spaces and their connection with primes. And then I give an idea of proof what we showed. So today it's the 27th of November. And in binary 27, you can write it as 16 plus 8 plus 0 plus 2 plus 1. So this gives the binary expansion of 27. But you can also combine these digits, and then you get the expansion in base 4. So by taking two digits, so 1, 1 gives you 3, 1, 0 gives you 2, and 0, 1 gives you 1. And then you have the representation in base 4. And in base 8, yeah, you combine 3 digits. So you have 1, 1 giving 3, and here you have also 0, 1, 1 giving also 3. And in base 16, for example, you have 11 plus 16, and since we only have 10 digits, I wrote B, so A for 10, B for 11, and so on. That's the usual convention. So this is for powers of 2. And the next power is 32, which is not so interesting because we only have a single digit, which is 27. But you can also do it in other bases, like 3, for example, or 5. Yeah, so in 3 you have 1, 0, 0, 0, and in 5 you have 1, 0, 2. And the question now is, can you do this in any base? Of course. I think you already learned this in high school, that if you take a positive integer q, and then you can represent every other positive integer n in a unique way as a sum of digits times the powers of the space. And here I didn't say that this sum should stop, but it is clear that at a certain point the powers are larger than n, and so the digits must be 0 from that point on. And so this is a unique representation, and we call it the q-adic expansion of the positive integer n. And if you are looking at the expansions, one way to analyze them is to look at functions that only look at the digits of the expansion. So these are functions f of n that only look at the digits of the expansion. And so we have, they are either q-additive, so if you sum this up, or they are q-multiplicative if you take the product of these evaluation at the digits. And if the evaluation is independent of the position of the digit, so here we have a dependency on the position. So if the q to the j is on the is not here, then we have a completely q-additive function. And a very famous example of a q-additive function is the sum of digits function. And the sum of digits function is, as its name indicates, it's the sum of the digits in the expansion q. And now we want to look at the relation of the digital expansion and prime numbers. And the first thing we could ask ourselves is, are primes recognizable? So what does this mean? This means that we have an automaton that takes the q-adic expansion of a number, and it says yes if it's a prime and no if it's not a prime. And yeah, as you think, if this would be the case, then the talk would be over now. But no, in 66 already it was proven that there is no finite Q automaton that can recognize the prime numbers by Minsky and Papert. And in 68, even for subsets or for infinite subsets, Hartmanis and Chunk, independently of Schützenberger, could prove that there is also no Q automaton that can recognize this infinite subset of primes. And this is somehow also related, the theorem of Cobham, that states the following. So if you have two bases, S and T, yeah, then and they are multiplicatively independent, so meaning that this means that S to the M equals T to the N has only the trivial solution M equal N equals 0. And that means that they are multiplicatively independent. And if you have these two, then the only recognizable the only sets that are recognizable with respect to these two multiplicatively independent bases are finite unions of arithmetic progressions. So they are really rather boring, yeah, because it's clear that you can detect or recognize arithmetic progressions by looking at the end of the expansion in which residue class the number falls, and so this is easy, but there is no hope that you get more than that. And moreover, in 1992, Mauduit could show that also the prime numbers are not recognizable by a morphism over the finite alphabet. And here I have two examples of morphisms that recognize certain sets. So this recognizes the squares, and this recognizes the powers of 2. And why is it possible for the squares? For the squares, it's possible because you know the distance between two squares. So if you have n squared and you have n plus 1 squared, then n plus 1 is n squared plus 2n plus 1. So you know that there are two n numbers in between that are not squares. And this is something you can easily construct with an automaton, and also the same is true for the powers of 2. So here, in order to see it, you have to start with A and then B and so on. And so there's, on this front, there's no hope that we can easily detect prime numbers. But on the other hand, if we cannot detect them, then let's look if they are behaving like the average does. So if, and the first, or one of the first things in this respect is to look at the arithmetic mean of the sum of digits function. And when constructing normal numbers, you have to count the occurrences of a single digit and also of a digit block. And Shiokawa in 74 used this construction to show that the arithmetic mean of the sum of digits function, when the sum of digits function run over the primes, that this arithmetic mean is the expected one. So q minus 1 over 2 gives the mean of a single digit. Then pi of x is the number of primes up to x, and log x over log q is the length of the expansion of x in base q. And here you have some error term. And the next thing is, yeah, you can look at the distribution. First, you can also generalize this to pseudo polynomials, because yesterday in Vitaly Bergelsen talk he spoke about Hardy fields, and there was the question of arbitrary powers of arbitrary powers. So here we have a polynomial, or a polynomial-like function, where at least one exponent is not an integer. So we have a function that looks like a polynomial, but in fact it's not. And if you look at the sum of digits function of this function, so if you evaluate the primes in this function and you take the floor and you look at this sum of digits function, then you get also the expected mean. So again, the mean of the sum of digits function, the number of primes up to p, and here we have p to the beta 0. So beta 0 is the leading exponent, and we have this length of expansion. And so now this is for the arithmetic mean. And what can we say on the limit distribution? So for the limit distribution, we look at the sum of digits function evaluated at polynomials in primes. And if we subtract the mean, the corresponding mean, and here we have the standard deviation, and then this tends to the normal distribution. Yeah, and this was proven by Basile and Katay in 1995. And we can use this for another nice result, and which I want to present here. So Stolarski in 78, he analyzed the ratio of the sum of digits function. So if you have SQ of n to the h over SQ of n, and then because of the power h, you get here that the expansion is h times as long as the expansion in the denominator. And so you would expect that then there are many more digits, and so the lim sup of this ratio tends to plus infinity. And he conjectured that the lim inf is 0, and also something about the arithmetic mean of this ratio. And Leischram and Thomas Stoll in 2011, we could show that the lim inf is in fact 0, and together with Thomas Stoll, we could show that moreover this ratio is dense in the positive reals. So you can take any number, any positive number, and this is an accumulation point of this sequence. And what you need here is the fact that if you take q to the k, so you take the, and you subtract 1, then you have a lot of q minus 1s. Yeah, so this, if you subtract 1, then you have a lot of q minus 1s, and if you add 1, then you have but q of this one as only sum of digit 1. So you have here this difference, and you play around with this difference in order to get this result. But this, as you can imagine, is a special property of the q-adic expansion. Yeah, in canonical number systems or other number systems, this is not the case. And and the other result is for the arithmetic mean. And here we showed, using the result of Basile and Katay, that the arithmetic mean of this ratio, when you evaluate over polynomials, then this gives you the arithmetic mean of the sum of digits function. And you can play around, because the proof is very elementary. You can play around, and you get that this is the same if you take the prime numbers, or even you combine primes and integers. So this is very general, because it's very elementary. So back to our problem. So in a paper by Hennenfent, he considered the relation of the sum of digits function when evaluated over arithmetic means, arithmetic progressions. But so here you have the sum of digits function over an arithmetic progression, and you look in which residue class this sum of digits function falls. And here you get a certain independence of the sum of digits function. So this means, otherwise said, that the sum of digits function, the output of the sum of digits function is independent from the input. Yeah, if you evaluate in arithmetic progressions. And in arithmetic progressions, you get that they are uniformly distributed they are distributed in a uniform way in the residue classes, to say it. And here we have this strange condition, and the reason for this condition, this is not a topic of the function, this of the method. In fact, this comes from the rule of nines. So if you want to check if a number is divisible by 9, you look at its sum of digits. If the sum of digits is divisible by 9, then the number is divisible by 9, and this you can generalize to q-adic expansion. So the sum of digit expansion, so the sum of digits of n is congruent to n modulo q minus 1. So if they are not co-prime, so the modulus here is not co-prime with q minus 1, then you have also certain restrictions on D. In a subsequent paper of Hennenfent, he also analyzed this and wrote down this relation for general, so dropping this condition. But for our purpose, it's enough to consider if they are co-prime. And then in 96, Fourier and Madritsch were looking at almost primes. So Hennenfent conjectured that so the arithmetic progression, this is nothing else than a function of the form you have d times x plus r. Yeah, so you have this polynomial, and so a linear polynomial, very easy. And the question is, can you do this for polynomials of higher degree or for prime numbers? And the first step was in the direction of almost primes. So an almost prime is a number that is either a prime or a product of at most 2 primes. So in this case, with 2. And Fourier and Madritsch could show that if you look at the sum of digits function along these almost 2 primes, then you get a lower bound of the size x over log x. And yesterday in Gerald's talk, he was also introducing the almost primes, so the R almost primes, and we saw that the number of almost primes up to x is about x log x to the r minus 1 over r minus 1 factorial times log x. And here you can say that x and log x, they are there, but the log factor is missing. So this is also a log away from the expected mean, and we have a similar result. Yeah, but I will come to this later on. So we have here almost primes, and speaking of Gerald, then in 2006, Cecilia Tisch and Gerald Tenenbaum, they showed that if you take a polynomial of degree d with integer coefficients such that the positive integers are mapped to the positive integers, then if you look at the sum of digits function of this of the integers evaluated with this polynomial, then you get a lower bound of n to the minimum of 1 over and 2 over d factorial. And this was one of the first results with polynomials, and in 2010, Madritsch and Rivard could show that the sum of digits over the primes is good distributed in residue classes. So they looked at the sum of digits function over primes, and here we do not have this condition that m and q minus 1 are co-prime. So this is now encoded here. So if they are not co-prime, then you take them from a certain residue class, and you don't take all prime numbers, you take only a certain, because the others cannot be reached because of the rule of nines. And for polynomials, in the year after, in 2011, Drummond and Mauduit and Trevard, they considered polynomials with integer coefficients, so that the positive integers are mapped to the positive integers, and they considered the sum of digits function along these polynomials and with respect to an arithmetic progression. And here they get a result if the base is sufficiently large. Yeah, so if the base is a sufficiently larger prime number, then they can show this. So still up to now, I think it's open that you have this for squares. It's known for also by Mauduit and Trevard, but for cubes and higher powers, it's still open in general without this restriction. What is the distribution of the sum of digits function? And now I want to show a little bit on the ingredients of the proof. So if you take the prime numbers, then one classical method is to use Vaughan's identity. So you start with a sum over the prime numbers, and you get this double sum over products of m and n. And then in the next step, they use the van der Corput inequality, and with this inequality, you shift the sum of digits function in one of the parameters. So, and here they use that if r is small compared to n, if r is small compared to n, then only a small amount of the digits are changing. So if you take a huge number and you only add 3, then you only have a little change in the number, and so the what it's called the carry propagation, it terminates in almost all the cases, except you have many q minus 1s, then it accumulates. And after this, they do a cut, and in order to get a periodic function, and this periodic function, they do Fourier analysis with it. Yeah, so you have this Fourier transform of this function, and this function will also appear in our proof. That's the reason why I present it here. So this function, they need some kind of an L1 estimate, an L2 estimate, and a weighted L2 estimate, in order to make their proof go. So these are small ingredients, so there's a lot else, but in fact you need a L1 norm, and L2 norm, and the weighted L2 norm. And now let's switch to linear recurrent bases. So linear recurrent bases and their relation with prime numbers. So if you look at in the beginning, we had 27, and we had the different representations, and we always used powers of 2, of 4, 8, and so on. And can we use another sequence? And yeah, we could try. And so if you take the Fibonacci sequence, yeah, so the favorite sequence that is not a power sequence, then you have here the numbers 1, 2, 3, 5, and so on, and then you get the following representation for 27. So it's 1 times 21, 1 times 5, and 1 times 1. However, if you look at this more carefully, then you have several expansions, not only the one here. And the reason is since the Fibonacci numbers are not growing like the powers of 2 or the powers of 3, they grow like the golden mean, and the golden mean is between 1 and 2. So the powers are more close together, and you get overlaps. And in order to prevent these overlaps from happening, so you have an overlap, you can either take 1 times 5, or you take 1 times 2 and another times 3, which also gives 5. Yeah. So then you have another representation, and similarly for 21, you can take 8 plus 13 is also 21, and by convention you take the expansion that has no consecutive ones in the representation. So that's the reason why I put an F here. So this is the Fibonacci expansion, or the Zeckendorf expansion, as it is called. And here you have this restriction that you do not take two consecutive ones in the expansion. And an easy way to obtain this expansion is by a sort of a greedy algorithm. So you take the largest Fibonacci number that is smaller than or equal to 27, you subtract it, and with the rest you look for the largest, and so on and so on. And then you get exactly this expansion. And the other expansions, you have to work a little bit for them. And in general, you can look at linear recurrent spaces. So what are the ingredients here? So we have a linear recurrent sequence. So with a characteristic polynomial that's given, or in fact it's given here, yeah. And we have here the characteristic equation. And then you suppose that G naught is 1, and for the first elements of the sequence, where you do not use the recurrence, you need that the elements are larger than the elements you can already represent. Yeah, so that you do not have overlaps. And here, this lexicographic order, this is exactly the forbidden 1-1. Yeah, so you have 1 and 1 in the expansion, and you forbid this in the expansion to appear afterwards, so that there are no consecutive ones in the Zeckendorf expansion. And for arbitrary linear recurrent sequence, you do the same. And yeah, for the q-adic numbers, you have the representation that Gn plus 1 is Q-Gn. Yeah, so this really generalizes also the q-adic expansion from the beginning. And so for the rest of the talk, I will fix such a linear recurrent base, and in this linear recurrent base, as before, we can define q-additive functions. So in this case, they are called g-additive, and these are functions that only work on the digits of the expansion. So we have an n, we have its digits, and f operates on the digits. And if it's additive, then it takes the sum. If it's multiplicative, then we take the product. And if this is independent of the position, so if it's independent of G, then we call it completely additive, as in the previous case. And one famous example is the sum of digits function, which is defined in the following way. So you have the sum of digits of n is the sum of its digits. And in the story here starts in the late 80s, and with Pető and Grabner and Tichy, and they showed that the arithmetic mean of the sum of digits function. So here we have along the positive integers is as one expects. So this ZCG, this is a coefficient that depends on the linear recurrence. And here I didn't say what's alpha. Alpha is the dominant root of the characteristic polynomial. And so for the Zeckendorf expansion, it's the golden mean. And similarly to the g-adic expansions, you have powers of q, and here the elements of G are roughly like powers of alpha. So this gives the length of the expansion, and here you have a fluctuation, so a one periodic function that represents, if you start with length k digit, then you have 1 and a bunch of zeros, and then it goes on and on and on till you reach q minus 1 everywhere, and then it jumps over to 1. And this gives you a period, and the period goes with the length of the expansion. Yeah. So this explains this formula, and for a fixed sum of digits, Stefan Wagner could show that if you fix the sum of digit function, so say the sum of digit function is fixed to k, then he could show some local limit theorem in the arithmetic progression. So he has here an arithmetic progression. So you evaluate n along arithmetic progressions. You look if the sum of digit function of this n is fixed, and you subtract the mean, and if you subtract the mean, then you get this this local density theorem, and this uses methods, so the saddle point method and methods from the analysis of algorithms, for the Hennenfent result, Mario Lamperger and Jörg Dusswaldner could show that this also holds true in the case of linear recurrent spaces. So you take the sum of digits function, so the g-adic sum of digits function, you evaluate it along arithmetic progressions, and you look in what residue class the function falls, and you get that they are equally distributed in residue classes. And so also you get this independence of the input from the output of the input. So you put in an arithmetic progression, and the output is equally distributed among the arithmetic progressions. And here we have this restriction. This is the q-1 restriction from before. So you also get the rule of nines, and the rule of nines, this generalizes to the sum of the coefficients minus 1. This has to be co-prime with this s. Otherwise, you get restrictions on the possible residue classes Q, on the possible modulus Q. And together with Jörg Dusswaldner, we could show a Bomberi-Vinogradov type result in this context. So if you again take that this is co-prime with, so we have this q-1, this rule of nines condition, then you get that if you look at the distribution of the sum of digits function in residue classes, if you evaluate along an arithmetic progression with respect to no arithmetic progression, so the whole sequence, then this gives you so to say an error of the distribution, and you take 2 times the maximum, and you evaluate over the Q to up to a certain level, and then you get that this has the distribution that you would expect it should have, and the problem here is, or the thing here is that if you take the term of the second largest exponent, the coefficient of the second largest exponent, which is also called the trace of this polynomial, then if you let this go to infinity, you can prove that the level goes up to 1. And since the level is above 1/2, we also get the same result with the almost 2 primes as Fourier and Madritsch did. And in the last minutes, I want to take a look at our proofs and the obstacles we had. So the idea of proof is we take a look at this difference that we have to estimate, and we want to get rid of these congruences, and the usual way is by introducing exponential sums. So you have an exponential sum over the residue classes modulo S, the residue classes modulo Q, and here you have Q minus 1 because you subtract here the one that corresponds to no residue class here, so to 0. And here you have this exponential sum, and now we rearrange the terms, and we in fact we have to estimate this blue sum here, this blue sum where you have sum of digits function and the argument itself, and they are both in certain residue classes, so multiplied by rational numbers. And in general, we have a sum of this type, and here I sum up to z, to an arbitrary z, but it's quite easy to look at the g-adic expansion of z, and then it is enough to look only at z that are elements of the sequence. Yeah, and if you compare this with the Fourier transform we saw before, then they are quite similar. So you have here the sum of digits function, and we have here also the sum of digits function. Then here we have the argument, and here again we have the argument, and so they are very similar. And then it also says that if you can show this L1 and L2 norm for this Sn, then perhaps you can also successfully attack the distribution of primes in residue classes. But this is not so easy, and we want to first take a look at this function Sn, and recall that we have this definition, and we use the linear recurrence in order to rewrite it in a sum of a term that comes from the recurrence, and the sum which is not going up to Gn, but a smaller g, and a smaller element. And so by this we get here these sine functions. So this in fact these are sine functions. So the sinus cardinal, as it is said in French. And this poses exactly the problems that we have, and I want to show you in more detail how they arise. So if you do this, so you iterate this, yeah. So you do it once, then you do it twice, then a couple more, yeah. Then you have here a product of these ans. And in fact, you get a product of these ans, and here you have a sum with a smaller term here. And now you cannot get you try to get an estimate for this sum. So you try to get an estimate for this sum, and an L1 norm and an L1 norm. This is easy. This is more or less what was done by Mario Lamberger and Jörg Duswaldner. And so you have this L1, but for the L2, it's not so easy. And so we did a step back and we looked at the paper by Fourier and Madritsch. And for the almost primes, they needed not an L2 estimate. For the almost primes, an L infinity estimate was sufficient. So they applied then the large sieve, and L1 and L infinity estimate is enough. And so we looked at an L infinity estimate, and compared to the classical Q-adic case, this you have this sum here. Yeah, if you take a Q-adic, then you have degree 1, and you only have this this product without these sums. But in the end, this doesn't make a huge difference. It's more the fact that if you take, so here we have in base 8. In base 8, if you take this product and you look at two consecutive ones, then you see that the maximum here is aligned with the maximum there, and with the other maxima here, they are small. So here you only have that there's one maximum and they are aligned. Yeah, and you get this throughout the powers of 8, and also for other bases. You get this, that the maxima are aligned, and this makes it more easy to estimate the maximum of this product. But here you have that if you take a linear recurrence, then you do not have this anymore. So the maxima is not above the other, and so it wobbles around, it's shifting, and this makes the whole thing very unpleasant. And this is also the reason why we have to suppose that this 7 here is sufficiently large in order to obtain our result, because this number here, the trace, this gives the number of pumps on this function, and if there are many, then we have a very, very large one, and all the others are small. And this is if you take 30 here, for example, it's even so the difference is even larger. So you have a really huge maximum here, and the others are very, very small. And this we can use in order to estimate this product. And another way of estimating is we combine 2 of them, and we combine 3 of them, and then you can also look at the distribution and get an estimate. So by combining more and more, you can reduce this bound on the trace, this lower bound on the trace, and yeah, it seems that if you can compute everything, then you get to the Fibonacci case, but it is very hard and very computation intensive. So thank you very much for your attention.
Yeah, Manfred, thank you very much for this presentation of many digital results. So it's open for discussion. Are there questions, remarks from the audience? So I have a small question. You mentioned this more or less elementary results with Thomas Stoll and this density type and such things. This is for the sum of digits functions, or can this be extended to, say, automatic sequences, or at least Q-additive sequences, or what can be done there?
For automatic sequences, we didn't look at this.
I have no idea, but the proofs seem quite.
Yeah, it is quite tight to the q-adic expansion. So if you even if you take minus q, so you take a negative base, then it's not clear that you can do this because you do not have this relation anymore.
Okay, but maybe there are conditions on the automaton or whatever. So maybe this is a question for the discussion room.
For automatic sequence, I think you have to try. Yeah, we tried for canonical number systems, and there it was hopeless because if you subtract a little bit from a power of the base, you can land anywhere in the fractal. Yeah, so you have no control.
Okay, so
and here, so the
so it depends on the fundamental.
It depends on the fundamental.
Okay.
Yeah. You take for n, you take a polynomial with powers of q. Yeah, and if and certain negative coefficients. And if the coefficient, so in the lower case in n, you have a negative coefficient, then you get a large sum of digits function. And then you take the h power of this polynomial, and you choose the coefficients in a way that they are canceling out each other, and you only have positive coefficients in the power, and then you be in this case that it is small.
So you need some so you get equal weight on the digits and such things. Yeah. Okay. Yeah. So thank you. Are there other questions? We don't want to have here private discussions, but maybe some general questions, remarks, comments.
Maybe a small comment.
Yeah, Sari, good morning.
Good morning. It was just based on how do you say, analogies. The graph that you showed us of the exponential.
On the end.
Yeah, with the two. Yes.
This one.
Yes. So this resembles a lot the graph of some functions that Eisleitner and Benz-Borda and Zaferopoulos obtained when they looked at the Sadler products. So maybe I can send you a reference if you want, but maybe I don't know if it's a true comment or not.
So maybe Benze is among the audience. I cannot see his name at the moment, but yesterday he was. No, it's too early for him. Okay, good.
Yeah, perhaps. Okay, so anyway, I'll send you the reference.
Yeah. Thank you very much.
Thank you.